So we're looking at reviewing for our next exam, applications of derivatives and integration. And so the first thing that we looked at when we started the material for this test was absolute extrema. And that was on 6.6. So when we were looking at this, we had some continuous curve on a closed interval AB. And if we had a continuous curve on a closed interval AB, then there had to be some absolute max and absolute minimum in there. That could occur in between A and B, or it could occur at the endpoint, one of the endpoints of the interval. And so let's look at the following example. I did see one, I lost it. So let's say that you had f of x is equal to negative 2x cubed minus 2x squared plus 2x minus 1. And we want to find the absolute extrema if they exist and all the x where they occur on the given intervals. And we're given the interval that we're trying to find the absolute extrema is between -3 and 1. Okay, so the first step in this is we needed to find our critical numbers. And so we did that by looking at the first derivative and setting that equal to 0. Okay, so taking the derivative, we're bringing our exponent down front. So we have -2 times 3. X, subtract 1 from our exponent, so we get an x squared. Minus 2, the derivative of x squared is 2x. Plus the derivative of 2x is 2. And the derivative of a constant is 0. So we get that first derivative is equal to -6x squared minus 4x plus 2. So I need to find when this is equal to 0. And when you're finding your critical numbers, you might find some critical numbers that fall outside the interval that you're given, that we're trying to find the absolute extrema. And so if that is the case, then what you want to do is make sure that those aren't the ones that you're looking at. You exclude those. And so I'm trying to find when f prime of x is equal to 0. So I'm looking at when is -6 2x squared minus 4x plus 2 equal to 0. I'm going to pull out a -2 when I write this, because I notice that each term have a -2 in common. So if I factor out -2, when I'm writing this, I'm left with positive 3x squared plus 2x minus 1 equals 0. I'm hoping that this factors what's inside the parentheses, this 3x squared plus 2x minus 1. I can kind of do some work on the side. And I can use my AC method. So if I look at AC here, AC is -3. Is there anything that multiplies to a -3, but that would sum to my B value, which is 2? So 3 and -1 are two numbers that multiply to -3, add to positive 2. So this is where we rewrote our middle term. So this is 3x squared plus 3x minus x minus 1. We then factored by grouping. We could pull 3x out of the first two terms, leaving you out with x plus 1. We can factor out -1 from the last two terms. We get x plus 1. So this factors as x plus 1 times, if we pulled that out, we'd be left with 3x minus 1. Okay, so -2 is never equal to 0. And so that doesn't give us a value, but x plus 1 is equal to 0 when x equals -1. And 3x minus 1 equals 0 when x is 1/3. Add 1 to both sides when you set 3x minus 1 equal to 0, and then divide by 3. So these are critical numbers, and they are contained in our interval that we're looking at from -1 to 3. And so this is where, and we don't have to look to see if this is a max or a min at those values. We just need to look at plugging in our critical numbers and our inbounds to our original function to see what the number is. So you can make a chart. And so if we look at, we're going to need to look at -3. We're going to look at, oops. Yeah, we're going to have to look at -3. We're going to have to look at, this is where sorry, this is contained. My bound was not -1 to, it's a -3 to 1. And again, they're still contained. These are contained in this interval. -1, I'm just going smallest to largest, 1/3 and 1. So we got to go back and we got to plug these values into the function for x and figure out what our y value is. Okay, so if I cube -3, that's giving me a -27. -27 times the -2 out front here. So far we got 54 minus, well, -3 squared is 9. 9 times this 2, so -18 plus, well, 2 times -3, so this is really -6. Plus 2 times -3, which is, oh, we just did that, and then -1. Okay, so 54 minus 18 minus 6 minus 1. This gives us a value of 29. Okay, so go through now and plug in -1 wherever you see an x. Well, -1 cubed is -1 times this -2 out front is +2. -1 squared is 1 times this -2 out front is -2. 2 times -1, that's -2, and -1. So 2 minus 2 is 0, -2 minus 1 is -3. So when x is -1, y is -3. So now plugging in 1/3. Actually, let's just plug in 1 first, and then we'll come back to the 1/3. Because I can do 1 in my head. 1 cubed is 1 times -2 is -2. 1 squared is 1 times -2 is -2. 1 times 2, so this is +2 minus 1. So I got -4 plus 2 is -2. -2 minus 1 is -3. Okay, so now plugging in 1/3. So I have -2 times 1/3 quantity cubed. Well, 1/3 quantity cubed is 1/27. And then I have -2 all times 1/3 squared. 1/3 times 1/3 is 1/9. Plus 2 times 1/3 minus 1. Okay, so I notice I'm going to need a common denominator. My common denominator between 27, 9, and 3 is 27. And so when I rewrite this out, I'm going to rewrite it with common denominators. So I have negative 2 over 27 minus, well, I'm going to have to multiply this negative 2/9 by 3 over 3. And so that would give me negative 6 over 27. I'm going to have to multiply this 2/3 to get my common denominator by 9 over 9. So 2 times 9, so this is going to be positive 18 over 27. Minus, and then 1, I have to multiply that by 27 over 27. So I have negative 2 minus 6 is negative 8. Negative 8 plus 18 is positive 10. 10 minus 27 is negative 17. So it's negative 17 all over 27. Okay, so our absolute max is 29. And it occurs when x is negative 3. So our absolute max occurs at x equals negative 3. And so remember when we're looking at absolute max and absolute min, that was the y value of your function. And so this is 29. So our absolute min, so the smallest y value we get back is actually negative 3. And there's 2 values, which gives us a y value of negative 3. So we actually have 2 values, which give us absolute min. And so the absolute min is negative 3 and occurs when x equals negative 1 and 3. Okay, so you should be able to find absolute extrema. You're going to have to find your critical numbers by looking at the first derivative, finding where it's equal to 0, maybe even undefined. This one, it just wasn't undefined anywhere. And then you would need to plug in your critical numbers and your endpoints into the original function to see what is the greatest y value and what is the smallest y value to get the absolute max and absolute min. Okay, so another thing that we covered in this section was implicit differentiation. And that's where we were going through an implicit equation. So that was where you didn't have y all in terms of x, or where you had both variables on both sides of your equation, and it was either hard or impossible to isolate one variable in terms of the other. And if this was the case, then we could use what was called implicit differentiation. So the one thing that you had to be careful when you used implicit differentiation was that you had to be careful. When you took the derivative with respect to y, we had to think of that as using the chain rule. So we had to remember to multiply by the derivative of the inside, which we could just write as dy dx or f prime of x, depending on which you preferred. Okay, so let me pull out a problem for implicit differentiation. And I'm trying to come up with some that are giving us different tools to look at with taking derivatives. What if it was x squared plus, or x squared times y cubed plus 4xy equals 2. And direction said find dy dx. Okay, so looking at this, it's almost, I don't know if it's possible, but I could not get right now y by itself and get this in terms of y equals just in terms of x. And so we're going to use implicit differentiation. We just need to be careful though, because I noticed that we have an x squared times a y cubed. And so when we use implicit differentiation, we're going to have to use the product rule here. And then our next term, which is 4xy, we're also going to need to use the product rule. Okay, so let's go through it and take the derivative. So taking the derivative of x squared, because when we're doing the product rule, take the derivative of the first. So derivative of x squared is just 2x times the second function, which is y cubed, plus the first function, which is x squared, times the derivative of y cubed. So derivative of y cubed gives us back 3y squared. But we're taking this with respect to y, and so this is where we had to tack in this dy dx. Plus, so now we're using the product rule again. So derivative of 4x, well, that's just 4, times the second function y, plus the first function 4x, times the derivative of y. Well, the derivative of y is just 1, but this is in terms, we took the derivative with respect to y, so this is dy dx, is equal to the derivative of the constant, and the derivative of the constant is 0. Okay, so let's rewrite this. We're trying to get dy dx by itself. So we're going to try to get all the terms with dy dx on one side of the equation and all the terms without dy dx on the other side of the equation. So here we have 2xy cubed plus 3x squared y squared dy dx plus 4y plus 4x dy dx equals 0. Okay, so these terms with this dy dx are going to stay on the side of the equation, and we're going to pull that out of those two terms. So if I factored out dy dx from both of those terms that had it, you're left with...
Shouldn't that be 3y squared? Instead of 3x squared?
Right here?
Yeah.
I pulled the 3 out front.
Okay.
Yeah. So I just pulled it in front of the x squared just because usually you see the numbers in front. Okay, so pulling the dy dx, this would be then 3x squared y squared. And then plus pulling it out of here, this is a 4x is equal to, so getting the terms that didn't have the dy dx on the other side, we would have subtracted this 2xy cubed. We would have also subtracted this 4y, so minus 4y. So to get dy dx by itself, all we have to do now is divide by what's inside that parentheses. And so we get negative 2xy cubed minus 4y, all divided by this 3x squared y plus 4x. Okay. So this says find the equation of the tangent line. To the graph of the square root. Underneath the square root is 2y minus 4xy equals negative 22 at the point 3, 2. Okay, so they've actually done some of the work for us. We actually have the point on our tangent line. If we didn't have that point, they would have given us either the x or the y value, and we could have plugged that back into the original to find what the value of the other variable was. But we already got that point. We know for an equation of a tangent line, we need the slope of the line at that x value. And we can find the slope of the line at that x value by looking at the derivative. But looking at this, this equation is in terms of both x and y, and I can't isolate one. I guess I could in terms of the other. It would be easier though if I use implicit differentiation. And so I'm going to use implicit, and I'm going to rewrite the square root of 2y so that I don't have the radical, and I'm going to rewrite it with an exponent just to make taking the derivative easier. So this is 2y all raised to the 1/2 power minus 4xy equals negative 22. And so we're going to use implicit differentiation. And so when I take the derivative of 2y raised to the 1/2, so I'm using the chain rule. Chain rule says bring our power down front, which is 1/2, all of the inside, 2y, subtract 1 from our power, we get negative 1/2, times, don't forget the derivative of the inside. Derivative of the inside of 2y is just 2. And we took this derivative with respect to y, and so we have to put this dy dx, because y is a function in terms of x. Minus, be careful here because we need to use the product rule when we differentiate 4xy. And there's a negative in front of this, and so this negative, I need parentheses or brackets around this whole product rule, because that negative is going to have to distribute into that derivative. So taking the derivative of the first piece, 4x, that gives us 4, times the second piece, y, plus, so the first piece is 4x, times the derivative of y, which is 1, dy dx. Is equal to the derivative of negative 22 is 0. Okay, so I'm going to clean this up a little bit. So notice that on my first term, I have a 2 in my numerator over here and a 2 in my denominator. I do not cancel that 2 inside of the parentheses because it's raised to a power. So we can't cancel that, but we can cancel this 2 here with this 2 here. And then I'm going to rewrite 2y to the negative 1/2 power. This is the same thing as 1 over, make this exponent positive, 2y to the 1/2, which is same thing as 1 over the square root of 2y, dy dx. So distribute the negative. So this is minus 4y. This is minus 4x dy dx. Equals 0. Okay, so we got to figure out what dy dx is. We can do that right now, or we can go back and plug in values. So we know what our point is, the point on the line. That was the point 3, 2. Okay, let me just pause for a second. Okay, so I had to just kind of pause. Let's come back to this problem. We are going to go back in and we're going to plug in our values for either x and y, and we're going to solve for dy dx. We can do that now, or we can factor out dy dx, get everything to one side, and then plug them in. Either way, it doesn't matter. I'm just going to plug them in now. So we have 1 over the square root of 2 times y. I'm going to just put a parenthesis there, and our y value is 2. And then we have dy dx minus 4 times y, so put parentheses there and replace that with a 2. Minus 4, you see an x there, so we're going to replace that with a 3. Dy dx is equal to 0. And so we can simplify. Well, we have 1 over the square root of 4. Well, 1 over the square root of 4 is 1/2 dy dx minus 4 times 2 is 8 minus 4 times 3 is 12 dy dx is equal to 0. So let's add 8 to both sides of our equation to get dy dx by itself. And so I really have a 1/2 dy dx minus a 12 dy dx. So technically, we can think of this as like terms. I need a common denominator though in order to add those. And so I could multiply this 12 over 1 by 2 over 2. So I really have 1/2 dy dx minus 24/2 dy dx. Well, 1 minus 24, that's a negative 23. Oops. Negative 23 over 2 dy dx. Is equal to 8. So get dy dx by itself, we're going to divide by negative 23/2, or think of it as multiplying by the reciprocal. So if we multiply by negative 2 over 23. So we get dy dx is equal to negative 16 over 23. So this is our slope of our tangent line. And we had our point that we're given at 3, 2. So the equation of the line, we got to figure out what our b value, our y-intercept is. So if we plug back things into this y equals mx plus b, we can solve for b. So our y value is 2, is equal to our slope, which is negative 16 all over 23, times x, which is 3, plus b. So we get 2 is equal to negative, well, 3 times 16 is 48, so negative 48 over 23, plus b. Notice I'm going to need a common denominator when I get b by itself. So I get 23 over 23 times 2, that's 46 23rds. I'm going to add 48 23rds to both sides. And so b gives us, what is that? 94 over 23. So our equation of the line is y is equal to tangent line. At that point is y is equal to m, which we said was negative 16 over 23 times x plus b, and b was 94 over 23. So questions on that one?
Does it matter what form we use, y equals mx plus b or y minus y equals m times x minus x?
So you can use either form, the slope-intercept or the point-slope form, unless they specify what they want it in.
Okay.
I'm not sure what they have done in the past for my math lab.
It's pretty much been the y minus y. I think it's the
Y minus y sub 1 equals m times x minus x sub 1. Okay. Yeah, you can use that. If you feel more comfortable with that way, use that way. We looked at some optimization problems. So what if you had the total profit in tens of dollars from the sale of X hundred boxes of candy is given? So in profit in tens of dollars. From sale of X hundred candy is given by. Okay, so we're given that the profit P of X in tens of dollars is negative X cubed plus 10X squared minus 12X. So we want to find the number of boxes of candy that should be sold in order to produce a maximum profit.
So what does that say? It says of X hundred candy
Is
what?
Given by.
Oh, okay.
That's given. Think, yeah. Sloppy handwriting. And so you're trying to find the number of boxes of candy? That should be sold in order to maximize profit. Okay, so we need to look at the derivative, and we need to find out what values of X give us a maximum. And so looking at the derivative of P of X, we get back negative 3X squared plus derivative of 10X squared is 20X minus the derivative of 12x is 12. And so we're trying to look at when is this equal to 0? So I can try to factor this. I can use my quadratic formula. I'm not liking that. Yeah, not too bad of numbers. -3 times -12, that's positive 36. Anything multiply to 36 and add to 20. Well, 6 and 6 are not going to work. 36 and 1 aren't going to work. 2 and 18 work. Okay, so if I rewrote my middle term using those, I have -3x squared. 20x I'm going to write as 18x, so plus 18x plus 2x minus 12 equals 0. So I did that so I can factor by grouping. I can pull a -3x out of the first two terms. That would leave me with a positive x minus 6. And then I can pull a positive 2 out of the last two terms, which leaves me x minus 6. Whole part of doing that was so what was in the parentheses is the same. Pull out x minus 6, you're left with the -3x plus 2 is equal to 0. So looking when x minus 6 is equal to 0, x minus 6 is equal to 0 when x equals 6. Looking at when -3x plus 2 equals 0, well, if you subtract 2, we get -3x equals -2. Divide by -3, we get x is equal to 2/3. Okay, so we need to see if these are max or mins. So we can do this a couple different ways. We had the second derivative test, and we could take the second derivative and plug those numbers in to see if they are positive or negative. If it was positive, that told us it was concave up, and that was going to be a minimum value. If we plug it into the second derivative and it was negative, then it was concave down, and we could say that it was a maximum. If we got 0, then the test was inconclusive. So or we can look at putting down our critical numbers and testing numbers to see if we're increasing or decreasing on a function. I'm going to use the second derivative test, and I'm going to look at the second derivative of x, because I noticed that taking the second derivative wasn't too bad. So second derivative of p of x, well, the derivative of -3x squared, this gives me -6x. And the derivative of 20x, so that's plus 20. And the derivative of -12 is 0. So if we plug in 6, we want to see if this is a positive number or a negative number. So -6 times 6 plus 20. Well, that's -36 plus 20 is -16. This is less than 0. It was concave down here then. And that means that p equals 6. I'm sorry, x equals 6. A max occurs. If I look at the second derivative and I plug in my 2/3, well, this gives me -6 all times 2/3 plus 20. Well, 3 goes into -6 twice. So I get -4 plus 20. -4 plus 20 is positive 16. This is greater than 0, which tells me concave up. And then this would be a minimum. Okay, so x equals 2/3, a minimum occurs. And so I'm not wanting minimums. I'm looking at what maximizes my profit. So it said find the number of boxes of candy that should be sold to maximize the profit. Okay, so look at this. X is in terms of hundreds of candy. And so this, when we got 6, X equals 600 or 600 boxes of candy. Maximizes profit. So part B says find the maximum profit. So we want to look at plugging in. Well, X is in terms of hundreds. We're just going to plug in 6 for X. And so plugging this in, I need my original equation. Thanks. Let me just go back up here and grab it. Okay, so plugging in the 6 there, we have negative parentheses. We're gonna put in 6 there and cube it, plus 10 parentheses. We're gonna plug in 6 there and square it, minus 12 all times 6. So we get 6 cubed. 6 times 6 is 36. 36 times 6, this gives us 216. So this is equal to negative 216 plus 6 times 6 is 36 times 10 is 360 minus 12 times 6 is 72. Okay, so we have 360 minus 216 minus 72. This is going to give us back 72. Okay, so going back and reading what it told us that P of X was in tens of dollars. So the maximum profit we're going to have 72 times 10, so the maximum profit would be $720. Okay, so I'm thinking that we got pretty much through what we did in chapter 6. So integration. Let me just pull some out. So integration, we did definite integrals, we did substitution method, and we did definite integrals and substitution with definite integrals. So if it had asked you to integrate How about -4 divided by y cubed dy? Okay, so this is not quite in the form that we can integrate. And so we want to rewrite this so that that y cubed in the denominator is now up in the numerator. And once that's done, then we can use that general power rule when we take the antiderivative. And so we could rewrite this as the integral of -4y to the -3rd power dy. And so when we took the antiderivative, so let's just keep our coefficient -4. But when we take the antiderivative, we're adding 1 instead of subtracting 1 to our power. So -3 plus 1, all divided by our new power. So -3 plus 1 is -2, plus our constant c. And so here we have -2 goes into -4 twice. And so this gives us back 2, y to the -2 power plus c. So this is equal to 2 over y squared plus c. And that would be the antiderivative of -4y to the -3rd power. So if we had the integral of the square root of 5 natural log of z plus 3 all over z dz. Okay, so looking at that, I do not know how to integrate that. And so that should clue you in. If you don't have a clue, that you probably need to use U-Substitution. I don't know how to integrate a natural log. So if you see natural log in there, usually that should clue you in. That's what you should choose to be your U. I don't want it just to be the natural log of z because we have more underneath that radical. So if I can rewrite what's underneath that radical as just one term u, then we'll be good. So let's choose u to equal 5 natural log of z plus 3. Okay, so taking the derivative of both sides, doesn't want me to change colors. So the derivative of u is 1 du. The derivative of 5 natural log of z. Well, it's 5 times the derivative of natural log of z. Well, that's just 1 over z. So 5 times 1 over z plus the derivative of 3, which is 0. And we did this with respect to z, so dz. So I want to get dz by itself. We can multiply both sides by z over 5, the reciprocal of 5 over z. So this would be z over 5 dz. I'm sorry, du. Okay, so let's go back in and substitute. So we have the integral of the square root of u all over z times dz, but dz was z all over 5 du. So our z's cancel and we're left with, and I'm going to rewrite u to the square root of u as u to the 1/2 power. So we have the integral of u to the 1/2 power over 5. You can think of that as 1/5 times that du. So taking the antiderivative, you're going to add 1 to your exponent. So 1/2 plus 1. So 1/2 plus 2 over 2, that's 3/2. All over 5 divided by the new exponent. So I don't know if you guys, when you were doing your homework with these, a lot of times, when you were dividing by the new exponent and it was the fraction, it's the same thing as multiplying by the inverse of that fraction. So same thing as multiplying by 2/3. And then we need to add on our plus c. Okay, the problem is our original function was in terms of z, and so we need to rewrite this. So we have 2. I see u here, and so I'm going to rewrite that. That u is 5 natural log of z plus 3. And that was all raised to the 3/2 power. And then I have this plus c over here. 3 times 5 is not 10. I don't know where I got 10, but 3 times 5 down here is 15. I cannot cancel that 5 natural log of z or that plus 3. Cannot simplify with this 15. First of all, we're inside some parentheses raised to a power, but also we have summations of terms. Let's just rewrite this as a radical though. This is 2, so the 3/2 power is the square root of what was underneath 5 natural log of z plus 3. And that cube, you can put it either underneath that radical and cube that whole thing, or we can put it outside of the radical. They will give us the same result. All over 15 plus c. Okay. I'm just trying to find some good ones. Let me see. What about the integral bounded between 2 and 10 of x all over x minus 1 dx? Okay, so if those were swapped, if that numerator or denominator was swapped, I can go about and rewrite it. But they're not, and so I can't rewrite that as multiple fractions. I don't know how to integrate that. It looks like we want to use U-Substitution. I wish my colors worked. So you know what I'm going to do? I know they'll work if I leave this and come back in. So let me just do that real quick. Okay, so let's use U-Substitution. We're going to choose U. Let's choose it to be the denominator, x minus 1. So once you figure out what U is, this is where you had to take the derivative. So derivative of U is 1. So 1 du equals the derivative of x minus 1. Derivative of x is 1. And the derivative of negative 1 is 0. So, and then the dx. So if we go back in and we substitute. So right now, since we're substituting, and we're going to have to put x equals 2 here and x equals 10, because these are in terms of x and not u, just so that it reminds you. And then we're going to rewrite this. This is x in my numerator all over. Well, this is what I had chosen u to be. So all over u. And then dx is du. Okay, so we have a problem because we have still x and u in this, and nothing simplified or canceled out that x. So this is where you want to go back to what you let u equal x minus 1, and solve for x. So notice we can get x by itself by adding 1 to both sides. So x is the same thing as u minus or u plus 1. So we can go back in. X equals 2, x equals 10 for our bounds. Our x value though, that is u plus 1. All over u du. So this is where we can either change our bounds now in terms of u, and that way when we integrate, we won't have to go back and do substitution, or we can integrate, keep those bounds in terms of x, but after we integrate, we have to do the substitution for what u had been in terms of x before we do the substitution in here. Let's figure out what u would be so we don't have to do that. Plus, let's rewrite this. We need to manipulate this a little bit, the integrand, so that we can integrate. So let's look at when x is 10. We're plugging it back up into here. So when x is 10, we get u is equal to 10 minus 1, or u is going to equal 9. So our upper bound is 9. And then if we plug in 2, we get u is equal to x, which is 2 minus 1. So u would equal 1 here. So these are for u. And if you want to, we can put u equals. And let's break that down as 2 separate fractions. And so we have u over u, which is just 1, plus 1 over u. Parentheses around that whole thing to u. Okay, so we're integrating. Yeah.
How do we know when we're supposed to change our bounds?
You can either change them or not change them. If you change them, we don't have to do substitution back later. If we don't change them, then we have to change after we do the antiderivative. We have to change this in terms of x instead of u. So it really just depends on your preference as to do it now or later. It doesn't matter. You just have to make sure that you're plugging in the right values for the right variables. And we'll get the same result either way. That help?
Yeah.
So I think when I first was learning this, back, I'm not going to tell you how long ago, I preferred to do it later. But then after teaching it, I prefer to do it now. So really, it's up to you what you prefer. So taking the integral of 1, that's just u, plus, so this was the special one. If we had an exponent of -1, if we rewrote this 1 over u, this was u to the -1, that was that special case that we couldn't use that rule where we add 1 to our power, divide by that. Remember that it was a natural log that gave us, when we took the derivative, 1 over u. So the antiderivative of 1 over u is the natural log of u. I don't need absolute values there because I'm plugging in positive numbers. And we're evaluating this all from when x is 1 to x is 9. Okay, so remember you're plugging them in Okay, so this is where if you didn't change your bounds, this is where you would have to go back and replace what u was. So you'd have to go say this is the same thing as what? X minus 1 plus natural log of parentheses x minus 1. And then you would plug in the 0 and 10, or 2 and 10, whatever it was. Okay, so this would look...
I'm just curious how you got the 1 plus 1 over u parentheses.
Yeah. So, yeah, it's from this u plus 1 all over u. Notice that we can split this up. Because I have a single term in the denominator, I can break this up as u over u plus 1 over u. Right? If I have a common denominator.
Yeah, okay, I got it.
Okay, yeah, no, sometimes it's hard to see it. So thank you for asking. Any other questions? Okay, so we're looking at basically by the fundamental theorem of calculus, this is f of 9 minus capital F, and my derivative of 1. So plugging in 9 wherever we see a u, we get 9 plus the natural log of u, which is 9. And then we have minus. Be careful because there's more than one term, so we need parentheses around this whole thing when we plug in the last bound. So we're plugging in 1, we have 1 plus the natural log of 1. So 9 plus a natural log of 9. This would give me negative 1, so minus 1. And this is going to give me minus natural log of 1. Okay, so remember logs are just exponents. So natural logs are the base e. And so this is saying e to what power is 9? I don't know, is some decimal. But I do know what e to a power that would give me 1. E to the 0 power is 1. So I know that this is 0. And also I can combine like terms. I have a 9 minus a 1. So that's going to give me 8 plus the natural log of 9, which is our answer. More U-substitution. One more U-substitution with bounds. So what if you were going from 0 to 2 x squared parentheses 3x cubed plus 1 and a parentheses, and this is raised to the 1/3 power dx. Okay, so I cannot distribute that x squared because what's inside the parentheses is raised to a power. So I noticed that we don't have any rule that we can take the antiderivative when you have a product. And so we should figure out what u should be. So let's choose u to equal. Well, I notice if I choose it, what's inside the parentheses, when I take the derivative, I'm going to get an x squared, which is going to help me cancel out with this one out here. So let's choose u to be this 3x cubed plus 1. So derivative of u is 1. Du is equal to the derivative of 3x cubed is 9x squared. And the derivative of 1 is 0 dx. We want to rewrite dx in terms of du. So we would divide both sides by 9x squared, and we get dx then is the same thing as du over 9x squared. Let's change our bounds. So we have x equals 0. Again, u is equal to 3x cubed plus 1. So u is equal to 3 times 0 cubed plus 1, or u is equal to 1. So we have the integral when x was 0, u is 1. Now we have to look at when x is 2. So we get u is 3 times 2 cubed plus 1. U is 3 times 2 cubed. 2 cubed is 8. 3 times 8 is 24 plus 1. So u would have to be 25. Replacing things, I have x squared, u raised to the 1/3 power, times, and dx was du over 9x squared. So notice that our x squares cancel. Which we wanted. And we have the integral. We could pull the 1/9 out now. It actually might be easier if we do that. So let's pull it out. We have 1/9 times the integral from 1 to 25 of u to the 1/3 power du. Don't know why I keep doing that. Okay, so we have 1/9 antiderivative of u to the 1/3. So let's add 1 to our power. So 1/3 plus 3/3 is 4/3. Divide by that new power is the same thing as multiplying by the reciprocal. Divided by 4/3, it's the same thing as 3/4. And I'm evaluating this, right, from 1 to 25. So we can technically leave that 1/9 out front and plug in our bounds. So we have 3 u. U though is 25. I think it will be easier if you, maybe not. And this is raised to the 4/3. Or it's the same thing as the cubed root of 25 raised to the 4th. All over 4 minus, now plug in 1. It's only one term, so I don't have to worry about putting parentheses around this. So plugging in 1, we got 3 raise 1 to the 4/3 all over 4. Notice that we can actually factor out a 3. I guess we don't. I don't need to. We could actually pull out. So this is 1/9. Notice that they both have a 3/4 in common. So if I pull a 3/4 out of this first piece, I'm just left with the 25 to the 4/3 minus 1 to the 4/3. Well, 1 raised to any power is just 1. So I'm curious about that 25 to the 4/3. I notice this is the same thing as 25, or the cubed root of 25 to the 4th. I don't know how far they write this. Remember that 25 is 5 squared, right? So this is the same thing as the cubed root, 25, so that's 5 squared to the 4th. Power to power is multiplying. So we have the cubed root of 5 to the 8th I'm just seeing how many 5s I can pull out. Probably should have just looked at the answer to see if they left it in that form. Okay, they left it in that form. So we can leave it in that form or we can go further. I might as well write just because I did this. So this would have been 5 to the 6 times 5 squared. 5 to the 6, the cubed root of that would be 5 squared, which is 25. Cubed root, 25. Okay. And I just mentioned that the answer in the book, they didn't do that. We could, though, simplify. See how I pulled this 3/4 out? That 3 goes into this 9 3 times. And so we're left with, technically, 1 times 1 in the numerator, which is 1. 3 times 4, which is 12. All times this 25 to the 4/3. Or you can rewrite it minus 1. Just because I did, I'm going to rewrite it. So this is the same thing as 25 cubed root of 25 minus 1. Okay, so area. Area under curve, let me see. So you're given a graph. You're given that your y-intercept is at 100. You have like a semi-circle or a quarter of a circle kind of shape. And let's say that this is 10. Oops. Can it smooth? Okay, something like that. And then you have another piece that falls, so this falls below the curve. Like this. And it wants you to find the area between the curve. So they want you to find this area. And they tell you that y, your function, is equal to 100 minus x squared. Okay, so we can break this down. We know that the area above the curve is, when we look at the integral, we can look at the integral from our x values, are the bounds, from 0 to 10. And so we have this integral from 0 to 10 of our function, which is 100 minus x squared. And then we have to put dx. We want to add the area underneath the curve. The problem is that the area underneath the curve is going to give us a negative result. So to take care of that negative result, we can either subtract off that integral, or we can think of it as adding the absolute value of the integral from 10, and this is 11. Of our function 100 minus x squared dx. And our absolute value. Okay, so taking the antiderivative of 100 is just 100x. Minus the antiderivative of x squared is x cubed over 3. And we're evaluating this from 0 to 10. plus the whole absolute value. Take the antiderivative of this. This is 100x minus x cubed over 3. Absolute value of that, but we were evaluating that from 10 to 11. Okay, so plugging in 10 wherever you see an x, we get 100 all times 10 minus 10 cubed over 3. And then minus, well, if you plug in 0 wherever you see an x, you still get 0. Plus, so the absolute value of this whole thing. So now we're going to go back in and we're going to plug in 11 wherever we see an x. So we have 100 all times 11 minus 11 cubed all over 11 minus, we need parentheses around this whole thing when we plug in 10. So we have 100 all times 10 minus 10 cubed over 3. And our absolute value. Okay, so 100 times 10, that's 1,000. Minus 10 cubed, well, that's 1,000 over 3. Plus the absolute value. So 11 times 100. It's 1,100 minus 11 cubed. That's 1,331 over 3. So basically I would distribute my negative. And so negative times 100 times 10, that's minus 1,000. And distribute my negative here, that's going to be plus 1,000 over 3. So I'm going to just keep this 1,000 for now, minus 1,003, 1,000 over 3, plus, so let's combine like terms inside of this absolute value. So 1,100 minus 1,000, that gives me 100. And then let's combine our negative 1,331 with our 1,000. So, and that's all over 3. That's going to give me a negative. And that will give me 331 all over 3. Okay, so I notice I need a common denominator. Might as well. So this is 3,000 over 3 minus 1,000 over 3. This is 2,000 over 3 outside of the absolute value, plus, so this would be 300 over 3 minus 331 over 3, which is negative 31 over 3. Which, if we didn't get a negative result, then we probably should know something's wrong because we were given that fell underneath the curve there. So this is the same thing as 2,000 over 3 plus 31 over 3, which is 2,031 over 3, which goes in evenly. Which is 677. It doesn't tell me what my units are. but I'm finding area. So area squared. Okay, so area under a curve. If it's talking about the area under the curve, you have to see if it's crossing the x-axis or not. You have to see if that curve is bounded between the curve and above the x-axis, or the x-axis and the curve. So if it fell below like it did, we have to take in consideration of the absolute value of that value. If it was not talking about area though, then you don't have to worry about where it's falling above or below. So I pretty much believe we went through a lot of what's on the test. I'm trying to think if there's anything else that I missed.